We've already kind of talked about this a little bit, this whole idea of how did our solar system form. By the way, in Unit 2, we're basically going to talk about how our solar system formed, kind of the nuts and bolts. We're also going to talk about the planets, which is kind of exciting. And then we're also going to, and I think I'll open up the planet so you guys be thinking about it. When we start in each planet, I'm going to open it up to tell me what you think you know or what you do know. You're probably correct, what you know about each of the planets. And then we're going to switch gears and we're going to talk about telescopes, ultimately leading up to telescopes. We need to talk about light and all that. But here's a picture of, this would be, we're going to lead up to this. This would be maybe our star or another star. And I kind of already talked about the snowball part a little bit. The idea that basically the way we got the planets to be is kind of it basically in a region around the sun. It kind of ate all of its material around the sun. That's why Pluto failed to clear its orbit of the debris. So this would be an early picture of maybe our sun or another star. And what you're looking at it is kind of what I said, face on, okay? Because it's flat, it's like a Frisbee. If you're looking at edge on, it looks like a line. So, so I'm gonna dim the lights a little bit. So this is kind of what we have now. That was what we had at one point. This is what we have now. So you would tell, and didn't make it to the test this time, did it? The plane of the ecliptic is basically what the Frisbee or the record player or the disc or whatever that the planets orbit the sun on. So in the scientific method, we talk about observations, and that's one of our observations, and then we talk about explanations for our observations. We can come up with hypotheses, test our hypotheses, and test and test and test, and then we can elevate our hypothesis to a theory. So that's one of our observations. Another observation is that the planets, this is my sun, the planets go around the sun counterclockwise. The planets orbit the sun counterclockwise. Now, I'm going to go ahead and tell you how that kind of came to be, that basically the cloud that ultimately made the sun and the planets had a bit of rotation counterclockwise, and it's been that ever since. It had to conserve that motion. So that's kind of how we got that motion. And then the other thing, we'll talk more about this, is when we talked about the orders of the planets, you guys told me that we had Mars, then we had the asteroid belt, and then we had Jupiter. What's the difference between Mars and Jupiter? What do you think? Just comes to mind. Can you picture Jupiter? How big is Jupiter? It's really big. Jupiter's very big. And then can you picture Mars? Small. What color is Mars? Red. It is red. It is red. Have we ever landed anything on Mars?
Yes.
Definitely. We have rovers going on Mars. It's a very busy place. Have we landed anything on Jupiter? We have actually, though, sent a spacecraft through Jupiter's clouds and atmosphere. Okay. The problem with Jupiter is it's a gas giant. The problem with Jupiter, yeah. Well, that's a big difference between Jupiter and Mars. So actually at that break, it kind of breaks our planets down into, like this says, the inner rocky planets ending with Mars, and then the outer gaseous planets beginning with Jupiter. We're kind of balanced about that whole thing. We got 4 and 4. But, so what are our outer planets? We got Jupiter. What's after Jupiter? Saturn, Uranus, and Neptune. Yep. And I'm going to stop there because is Pluto a planet? No. But can you kind of see a little bit where Pluto actually just does not fit in with those 4 that precede it? Okay, so yeah, when we talk about how did our solar system get to be what it is, we have to take those observations into account. And this slide kind of says that too. Okay, so the planets all go around the sun counterclockwise. Now, Does Earth spin on an axis of rotation? How long does it take to complete one spin, one rotation? About 24 hours. Was it always 24 hours? No. It used to be faster and it's slowing down as we speak. The spin. So Earth orbits the sun counterclockwise and it spins on its axis counterclockwise. And that works. Actually, so what's the planet beyond, what's after, am I saying this right? No, sorry. What's the planet closer to the sun than the Earth?
Wait, what?
What's the one planet closer to the sun than the Earth?
Venus.
Venus, it is Venus. And the thing about Venus, it's kind of Venus goes around the sun counterclockwise, but Venus on its axis of rotation spins clockwise. We'll talk about why that is. So really? But most of the other planets, you go see them, they orbit counterclockwise, they spin counterclockwise. It just seems like a natural thing, you know, in the same direction. This kind of breaks down what we were talking about the two types of planets. So the break is like at the asteroid belt, isn't it, between Mars and Jupiter. So if we were to kind of compare and contrast, what does it mean that what does low density mean to you guys?
Like they're not as big.
They're thin, yeah. They're not as kind of massive squished together. They're thinner, yeah. And that kind of goes to when trying to land a rover on Jupiter, you got problems because there's no surface. Basically, the surface is gas. Yeah. One thing in my slides I want to point out that it says Jovian planets, but this is our gas giants, same thing. Then you're going to have to kind of be able to go back and forth. Terrestrial are our rocky planets.
So Jupiter's just a big cloud, pretty much.
It gets more and more compact as you go closer to the center of Jupiter. But yeah, the outer parts are clouds. They're clouds. They're just like
you can't actually land on it. You just can't go through it.
Mm-hmm. Yes and no, because when we study the gas giants, beginning with Jupiter, Saturn, Uranus, and Neptune, all of the gas giants actually in their core, it's like they swallowed a terrestrial planet. They didn't really swallow a terrestrial planet, but there is actually a rocky pit in the center of each one of those gas giants. Yeah, and it has to do with kind of how they formed. So the thing about it is the closer you get to the center of Jupiter, I started to say this, the more and more compact the molecules are, the matter is. And one of the things about matter is that you can take a gas, and if you compress it enough, you'll get a liquid. And you can take a liquid, and for most liquids, if you compress it enough, you'll get a solid. So the pressure increases as you go towards the center of Jupiter, as you go towards the center of the Earth. It's all the same thing in that sense. Yeah, so I sometimes low density, sometimes I'll call this fluffy. They're relatively low density, no solid surface. So moons, for the rocky planets, let's take a survey. Does Mercury have a moon?
Yes.
No. Mercury has no moon. Mercury has no cute little Mercury. Yeah, Mercury's the planet closest to the sun, and when we see pictures of Mercury, Mercury kind of looks like the moon. It's pretty little. Venus. Does Venus have a moon?
No.
No, correct. Venus does not have a moon. Does Earth have a moon?
Yes.
Yes. How many moons?
We have one.
Only one. Do you guys remember, does Mars have any moons?
No.
Yeah, it does.
It's got two ugly ones that it kind of captured, kind of accidentally stumbled around Mars, and they've been there ever since. Probably little asteroids. They're like little asteroids. Phobos and Deimos, yeah. Yeah, so Mars. So, does Jupiter have moons? Yeah. Saturn has moons, Uranus has moons, and Neptune has moons. So all of these gas giants have moons. Does Saturn have a ring? Yes. And I'm here to tell you that Jupiter has a ring too.
Yeah, it does.
It's
really light.
It is very light.
I see it, but it's there.
It is. And Uranus has a ring, and Saturn has a ring. When I say a ring, it's rings, series of rings.
I thought Neptune had a ring.
Yeah, Neptune, Uranus, Neptune, Uranus, Jupiter, and Saturn. Yeah. So here's one thing for you, and this is part of the key to understanding kind of our solar system formation. Where is it going to be warmer? Right here, or is it going to be warmer out here?
Oh, next to it.
Yeah, it's going to be warmer next to the sun. Exactly.
Mercury's like 500 degrees in the daytime.
It is very, very hot. Mercury's very, very hot. The daytime, the nighttime side of Mercury is really cold though, because it's so slow.
Below.
It's very. So it's hotter here, and actually that's an important aspect of understanding why these guys. Now here's one thing for you. So if you take water and you heat it up, let's say beyond boiling, what happens to the water? It evaporates, exactly. So here, we're not going to have, we have water actually this close to the sun. Earth's got a lot of water. But the closer you are to the sun, the more likely you're going to have a hard time keeping your liquids. Heck, you're going to have a hard time keeping your solids. And so that's kind of the way that all worked. So this sometimes makes it to my test as a term. Okay. A nebula, I don't know if you guys, I think I've mentioned what a nebula is. Usually to mention what a nebula is, I usually start out with saying, if you are in outer space driving between stars, like from our sun to Sirius, the star Sirius, most of what you drive through is going to be nothing, no atoms of anything. And sometimes you'll run into a cloud that's called a nebula. And actually through our telescope we can see these nebula. Some of them glow, and some of them don't glow. So if you are in a space, if you're in a region of space that has some stuff, moderate amount of stuff, you are in a nebula. So when we talk about the formation of our sun and the planets, collectively called our solar system, it actually was born out of what's called the solar nebula. There was only one solar nebula because the word sol refers to our sun. Okay, so one solar nebula. Now, the thing about, and then you'll be like, a natural thing would be like, all right, so why was the solar nebula there? Why is that nebula there? Why is that nebula there? And it all has to do with stars that have lived their lives, and we'll talk about star cycles, but stars that have lived their lives, and some stars blow up. In fact, you've heard that before. That's called a supernova. Some stars blow up, and they leave their stuff, and that's like a nebula. They leave their stuff there. Not all stars blow up. Some stars and our star won't blow up. It just kind of creates matter. It doesn't create matter. Well, it creates stuff through its life, and then it just kind of lets the stuff kind of flow off of it, and that's another way to get a nebula. So my point is, this solar nebula actually came from another star, our solar nebula, and we've actually got there's more than one way to look at what supports that. Okay, so our solar nebula came from another star, and this is a picture to kind of walk you through what that would look like. So let's see. Let's start with this guy. I'll put a 1 here. And I don't know if you can kind of tell, this is like a disc that's kind of like a frisbee. And you see kind of the hot region here is going to become a star. And it can kind of create these jets of material that kind of come, what we say, perpendicular from its disc, okay? So this is its disk and stuff. This is like going to be a baby star. Baby star. It's not alive yet. And so it's a nebula, stuff coming together, especially in the middle to create the star. And it shoots out jets of material. So this then actually is, as it is a star, okay? This is when it is a star. And this says it's creating heavier and heavier elements. We'll talk more about that. And this then actually, this is a dying star, and this is creating the nebula that can be recycled into a new star. So that's kind of how that goes. Now, I don't like the word. I would call this stellar recycling. I would. But they call it galactic recycling, like galaxy recycling. But actually, it's the star living its life and then giving its material back. So this is really morbid, you guys. Oh, I'm not gonna. Yeah, I can. So it's like dust to dust. As we die, we decay. And I'll change it. Won't be so morbid. But you know that you can actually go ahead and get these pods now, where after you die, you're put in a pod, and maybe a tree or something is planted, and you are recycled back into life. And I'm just like, this is really cool. That sounds awesome. You know? You like
So when you die, they're gonna put you in this thing.
And I'm gonna be a plant.
Plant a tree on top of you in the soil,
That's
and then
awesome.
like the stuff from your body gives the tree nutrients, so then it grows.
You're not seeing it. I think it's so cool. I don't know.
I mean, I can't see that in the back of my yard. Back of my yard, that's my house. I say house. It's my tree, and my kids or my grandkids. So.
There are some things, but it's interesting because as it is, and actually the morbid part I was going to say, my dad passed away several years ago, and one of my first thought was, he was a jokester, and I'm like, he'd like the thought that he's like going to be feeding the worms, I don't know.
How he's dead.
Yeah, because he would he's like, don't make it to do, let me go feed the night crawlers. So I don't know, we didn't do that. But
It'd be different from the people that keep their ashes on the mantle in their house.
yeah.
I mean, it's about the same thing.
Yeah.
That is true.
I don't know.
Or like some people wear like the lashes around their necklace.
Mm-hmm.
My auntie got one.
Mm-hmm. So we're all so different, but I just think that's a neat thought. And galactic or something. So anyway, all right. So solar nebula, all right. It may or may not be on the test. The word nebula we're going to run into later. We actually, the other day when we had the telescope set up, did we look at a nebula? We tried. I don't think we really saw it. Yes. Yeah. But there are things we can point our telescope to that are nebula. But the solar nebula was the precursor to our solar system. Now, does this kind of make sense? Like, picture that won't work. I was going to say picture our moon getting hit by all those little rocks and causing craters on our moon. But can't quite go there yet. So there's our solar nebula. I'm going to kind of talk you through step by step what that would look like. So, is this right? Yeah. In this class, I get this class in one of my other classes mixed up because early on we talked about the same things. But we said you can convert potential energy into kinetic energy is what's done with a cloud. Remember we talked about that. If a cloud is big, it's got a lot of potential energy, not much kinetic energy. What happens as a cloud comes together? What happens?
It's more and more kinetic and less potential.
Right, exactly. More and more kinetic, less potential. So that's actually what happened to our solar nebula. It used to be this big. And actually, if you look at what our current solar system is about, what's out there now? Press letter C. Comets. That's what I was after. Yeah, what's out there now is just comets, yeah. So, but our solar system used to be widespread. The solar nebula was big. It contracted, just like you said, it heated up. Now, the thing about gravity is that where's the gravity the strongest in our solar system right now? What's that?
Sun?
Yes. Gravity, the thing for gravity work is the more massive something is, the more gravity it has. So this is definitely the most massive object in our solar system. Yes. And so actually that's not an accident. So when that cloud was forming our solar system, most of the material actually fell in the middle to become this object we call the sun. Okay. So solar nebula, sun. And in the meantime, as it was doing that, like this slide says, it had a certain amount of spin. What direction was that solar nebula spinning? Counterclockwise. It's been that way ever since, exactly. So if you kind of compare 2 and 3, what's the difference?
They kind of became somewhat objects now.
Mhm.
They're not just clouds.
Yep, objects. They're kind of creating objects in a lane of sorts, aren't they? It's like a track creating a lane. And you can't tell it, but this object here, okay, what happened to its size?
It got smaller.
It got smaller. Now, that doesn't mean it lost any mass. It got smaller because it's squishing together, squishing together, squishing together, squishing together.
And I guess once it got small enough, the other stuff started, I guess, piece together around it as it was
Mm-hmm. Yep. You can kind of start to see some lanes, and these things are piecing together. So what's the difference here?
You have definitive objects, I guess, going
Mhm.
around it. No.
Exactly, definitive objects. I like that word. So you can kind of see the caption. I don't know if you guys can read it out there. Those definitive objects, these things, okay, those are called, they're adorable. I love this word. They're called planetismals. Planetismals. If you have a prototype, what do you have? Is it
It's like still in development.
still in development? Exactly. Prototype still in development. This thing is now called, this is called the proto-sun. So do you think it's a full-fledged sun yet? No. So those are planetismals. So this is a good place to end. We'll pick up here on Monday.